Here's example 4 with applied optimization. So again, if you want a copy of this worksheet and a copy of these steps that we're going to follow, go ahead and check the video description. There's going to be a link, so you can click the link, open up this worksheet, download, print it if you want. Okay, so here a Norman window is constructed by adjoining a semicircular window to the top of a rectangular window. And if the total perimeter of a Norman window is 28 feet, what is the maximum possible area? Okay. So always read the question first completely, and then so step 1 here, draw and label the picture if possible, and assign variables to all quantities in the problem. Okay, so now problems about Norman windows usually come with a picture, but you know, this one's described here, so it doesn't really matter. But what we have is a semicircular window sitting on top of a rectangular window. So let's go ahead and draw that. Okay, so we just have a rectangular window here, kind of sort of, and then on top of that we have a semicircular window. Okay. That could have gone a little better. Okay, so now we want to label the picture, right? So we can really call these anything we want, but let's label this X. Okay, so this side's going to be X. Now we could label this side something, but to make it easier on ourselves later, let's just call this R. Okay, because that's the radius of the semicircle. So if this is R, okay, this distance here halfway across is R, and if this whole thing is a rectangle, then this distance here is going to be 2R, right? Because half of the distance is R, this is a rectangle, so this has to be 2R here. Okay? So then also, since this is a rectangle, this is also X over here. Okay, so there's a picture, we just drew it and labeled it. Now we want to assign variables to all quantities in the problem. So you know, we want to write down what those are, but here X could be the length or the width, whatever you want to call it, of the rectangle. R is the radius of the semicircular window here. So you know, we already have these labels, so let's not really bother to write them down. Okay, so now what else do we have? We have a perimeter, but it's not really a variable. It's a constant 28 feet, so we don't have to assign it any variable or anything. But we do also have an area. Okay, the area is what we want to mess around with and try to maximize. We want to get the maximum possible area. So let's call that something. Let's say, let capital A be the area of the Norman window. Okay, so that's step 1. Draw and label the picture if possible, and assign variables to all quantities in the problem. Now step 2, write an equation for the quantity to be maximized or minimized. So what we want to do is maximize this area A. Okay, so the area of this whole Norman window is the area of the rectangular piece plus the area of the semicircular piece. Okay, so the area is going to be, now what's the area of the rectangular piece? It's just length times width, right? So in other words, 2R times X. Okay, that gives us the area of the rectangular piece. Now what about the semicircular piece? So we have to add that to this. We have to add the area of the semicircular piece to this. So, so remember from geometry, the area of a circle with radius r. Okay, so for a circle with radius r, the area is pi r squared, right? But that's for a circle with radius r. What we have is a semicircle, which is just half of a circle, right? So what we want to do is take pi r squared divided by 2. Okay, that's going to give us the area of a semicircle with radius r. Okay, because we have half a circle here, so we take pi r squared and divide it by 2. Okay, so that's going to be the area of this entire Norman window. 2rx for the rectangular piece, and then we add pi r squared over 2 for the semicircular piece. Okay, so that's the area there. And that's really it for step 2. Write an equation for the quantity to be maximized or minimized. Now step 3, reduce the equation to one with a single independent variable, and this may require secondary equations that relate the variables to each other. All right. So remember, this is the step where we ask ourselves, okay, do we have any other information that we could use to relate r and x to each other? And yeah, you know, what else do we know? We have the stuff about the perimeter that we haven't used yet. So now the total perimeter is 28 feet. Okay, so what we want to do is just use our picture here, okay, and our variables x and r to write an equation describing the perimeter. So the perimeter is just all the outside stuff, right? So that's this piece plus this piece plus this piece, and then plus the semicircular piece out here, but not this piece in here, not this piece, because this is not part of the perimeter because it's not on the outside. Okay, so don't add this piece here, just forget about that piece completely. All we have is x plus 2r plus x, so let's write that down. X plus 2r plus x, and then we add this part out here, the perimeter, I guess the circumference really of the semicircle out here. So remember, for a circle with radius r, the perimeter or the circumference is 2 pi r. Okay, but we have a semicircle, which is half a circle. So we take this perimeter divided by 2. Okay, take the circumference or perimeter and divide it by 2. So then we do plus 2 pi r and then divide it by 2. Okay. So x plus 2r plus x, that's this, x plus 2r plus x, and then plus 2 pi r over 2 gives us this piece out here. Okay? And remember, we don't add this piece in here, so we don't add another 2r. We only have the one 2r, okay? Only one of those from this piece here, and don't add that. So make sure to keep that in mind. And then we're told that this equals 28. Okay, we're told that equals 28. Okay, so that's good. All right, now what we want to do is simplify this equation, mess with it a little bit so that we can express one of these variables in terms of the other. Now, let's look at this equation here and see, okay, 2rx plus pi r squared over 2. It's going to be easier to get x in terms of r, so that when we substitute into this equation, we only have to worry about this one piece right here. Now, if we get r in terms of x, it'll still work, we can still do that, but it's going to be a little more complicated because we have this r squared here, so we'll have to square our expression in terms of x. So let's not do that. Let's just solve this equation for x in terms of r and stick it into here. Okay. All right, so x plus 2r plus x, that's 2x plus 2r. 2 pi r over 2 is just pi r, and then that equals 28. Okay, so we're solving this for x. Now again, we could solve it for r, but it's going to be a little more work, just more than we really want to do or need to do. So 2x. So let's subtract 2r and pi r from both sides. So this is going to be 28 minus 2r minus pi r. Okay. Now divide everything by 2. Okay, so divide by 2, divide it all by 2. So 2x over 2 is just x, of course. And then 28 over 2 is 14. Minus 2r over 2 is minus r. Minus pi r over 2 is minus pi over 2 times r. Okay? So this is our expression for x in terms of r. So now what we're going to do is take this guy and stick it on up into this equation over here. Okay, so we can take this, stick it on up into this equation here. And then what we're going to have is an equation for the area A in terms of just r. Okay, so the x is going to go away because what we just found out here was that, if we have a value for r, we can get a value for x using this equation. So in other words, x and r are always related by this equation here. So we're just going to take this, stick it into here, and then x disappears from this equation, which is what we want for step 3. Okay? So reduce an equation to one with a single independent variable, and that's what we're doing. So now a of r equals 2r, so we still have the 2r here, and then this x becomes 14 minus r minus pi over 2r. 14 minus r minus pi over 2r. Okay? And then we still have plus pi r squared over 2. So let's rewrite this as pi over 2 r squared like that. Okay? No real reason for doing that, just, keep it consistent, I guess. Okay, so now a of r equals, let's simplify this a little bit. So distribute the 2r, we get 28r minus 2r squared, and then here minus 2r times pi over 2r, so this is going to be, the 2's are going to cancel, and we still have pi and r left, so it's going to be minus pi r squared, and then plus pi over 2r squared. Okay? So minus pi r squared plus pi over 2r squared, so this is going to be a of r equals 28r minus 2r squared, and then this becomes minus pi over 2 r squared. Okay? So if you're not sure about that, let's come up here real quick. So minus pi r squared plus pi over 2 r squared. Okay, this is what we want to simplify here. So there's a common factor of r squared we can pull out, so let's go ahead and do that. So this equals minus pi plus pi over 2. Okay, that quantity times r squared, right? So we just factored out the r squared here. Now pi is just 2 pi over 2, right? So minus 2 pi over 2 plus 1 pi over 2, so that's going to be minus 1 pi over 2, in other words minus pi over 2, times that r squared. Okay, so that's just what happened there, just the details there in case you're not sure. But anyway, that's where this minus pi over 2 r squared comes from. So that's it for step 3, reduce the equation to one with a single independent variable. Okay, and we used, so this may require secondary equations that relate the variables to each other. So this is our secondary equation here, describing the perimeter. So this related x and r to each other like this. We use this, stuck it into our area equation to get the area equation in terms of just r. So now we can do calculus on this. Okay, but before that, before we start doing calculus, we want to know what's the domain of the equation found in step 3. Okay? So again, we want to be careful with the domains, because if we just look at this equation, just forget about the application, look at the equation, there's no domain restriction here, right? It's just a polynomial. Here's an r squared, another r squared. So nothing there, but we are restricted by the geometry of the problem. So the restrictions that we have are r has to be strictly positive because it represents a distance or a length, and the same thing with x. X represents a distance or a length, so it has to be strictly positive. Now, so the domain restrictions, r has to be strictly positive, and also x has to be strictly positive. But our domain has to be expressed just in terms of r, okay? Because the area equation is in terms of r, so our domain has to be expressed just in terms of r. So r greater than 0 is okay, but this, we have to express this in terms of r. Well, how can we do that? Well, we can use this equation here. Okay, so x has to be greater than 0, but x is this, so 14 minus r minus pi over 2r has to be strictly greater than 0. Okay? So let's add r and pi over 2r to both sides. So 14 has to be greater than r plus pi over 2r. Now what we really want to do is solve this for r. So 14 has to be greater than, this is 1r, right, plus pi over 2r. So let's pull out the r, and we're going to have 1 plus pi over 2 left. Okay. Now divide both sides by 1 plus pi over 2. And then we're going to have 14 over 1 plus pi over 2 is greater than r. Okay, so that's our restriction for r. So this restriction, x greater than 0, becomes, or is the exact same thing as this restriction here. Okay? So complex fractions like that, or compound fractions, whatever you want to call them, they're not really, we don't really like those, we don't really want to have those. So let's multiply the top and the bottom by 2. Okay? So if we multiply the bottom by 2, that's going to kill the pi over 2 here, and then we have to do the same thing to the top. So that's going to be 28 over 2 plus pi. Okay? It has to be strictly greater than r. Okay? And again, the reason we have this restriction here, the reason we have this is because x has to be strictly positive, because x represents a length or a distance, so it can't be negative and it can't be 0. And physically it could be 0, but then nothing's happening in the problem, we don't really want to deal with that. Okay, so depending on your instructor, they might say, yeah, x could be 0 or r could be 0, that's okay. Because physically that is possible, but then nothing's happening. Okay, there's nothing interesting happening with the problem, so we do want to toss that case out. But different people might have different thoughts on that. Okay, but whatever the case, r cannot be negative because that just can't physically be, and x can also not be negative, so that can't physically be. Okay, but anyway, just watch out for those little corner cases there. So, and again, the domain has to be expressed just in terms of r, so we can't say this. Okay, but x greater than 0 is the exact same thing as saying r is less than 28 over 2 plus pi. Okay? So this is the same thing as saying r is less than 28 over 2 plus pi. Okay? And 28 over 2 plus pi, that was about 5.446. 5.446-ish. Okay, so the domain in interval notation, that's going to be 0 to 28 over 2 plus pi. Okay, so you should be exact as much as you can, so we'll use this expression and not 5.446. Okay? Because this expression is exact and this is rounded out to 3 decimal places, and it's better to keep it exact as much as you can for as long as you can. So here's our domain, okay, for the problem. Okay, so now that's step 4, find the domain of the equation found in step 3. And again, the domain had to be expressed just in terms of r, which is why x greater than 0 is not okay. Okay? Not an okay answer to use for step 4. Okay, but we can use that fact combined with this equation to get this restriction here, okay, to get this. All right, now let's move on to step 5, use calculus techniques to find the desired quantity. So what we want to do is maximize the area. Okay, so now we're just going to do calculus here. So a of r equals 28r minus 2r squared minus pi over 2r squared. Oops, sorry about that. Okay, so now what we want to do is just, so we want to find the actual maximum value of a, so we're just going to take a derivative. Okay, so now from here, we can kind of forget about the application. Remember the domain though, forget about everything else that's happening and just start doing derivatives. So 28r, the derivative is 28, minus 2r squared, the derivative is minus 4r, minus pi over 2r squared, so that's going to be minus pi over 2 times 2r, so it's just minus pi r. Okay? So that's what's going on there. Now, we're trying to maximize the area, so what we want to do is find the critical points, right? That's why we took the derivative. We're looking for critical points. So we want to take this, set it equal to 0. Also, we want to find where the derivative is undefined, but this is never undefined, right? Because, it's just a polynomial, so it's never undefined. So just set it equal to 0, solve for r. So 28 equals 4r plus pi r. So in other words, 28 equals 4 plus pi, that quantity times r. So we're just factoring out the common factor of r here. Okay? And then divide both sides by 4 plus pi. And then we end up with, let's write it as r equals 28 over 4 plus pi. Okay, so first of all, we want to know, is this actually in the domain? So you can just kind of eyeball it and say, okay, that's our domain is capped at 28 over 2 plus pi. 28 over 4 plus pi, that's a larger denominator, so it's going to be a smaller number. So yeah, that's in the domain. But if you're not sure, you can just toss it into a calculator, and you're going to get about 3.92. Okay, so remember, this was about 5.446, and 3.92-ish is smaller than that. Yeah, about 3.921-ish if we round up to 3 decimals. So this is inside the domain, so that's good. But again, keep it like this. Don't use the approximate value. Use the exact value. Okay? Now, we want to make sure, so we want to use the first or second derivative test to make sure that this is actually going to give us a max. Now again, by the nature of the problem, most of the time it is going to give you what you want, but we do have to be thorough, be very careful here, make sure we're getting what we want. So we have to go all the way with this. Okay, so it's going to be better to use the second derivative test because the first derivative test, it'll work, but we have to set up that sign chart, we have to talk about increasing and decreasing, things like that. So it'll work, but it's more work than we need to do, and it tells us more than we want to know. So it's better to use the second derivative test. Okay, so a primed of r is 28 minus 4r minus pi r. So let's do the second derivative. So the second derivative is a double primed of r. So 28 becomes just 0. Minus 4r becomes minus 4, minus pi r becomes minus pi. So in other words, a double prime of r equals minus 4 minus pi. Okay? So now, but this is just a constant, right? So no matter what r is, the second derivative is always minus 4 minus pi. So this is actually really good because we don't have to worry about this goofy looking r here. So a double primed of 28 over 4 plus pi. Okay, so even though that's a really goofy expression for r, we don't have to worry about that because the second derivative is just a constant. So we have this. Now what kind of constant is that? Minus 4 minus pi, that's a negative number, right? So remember, pi is about 3.14-ish. So minus 4 minus 3.14-ish, so it's about minus 7.14 something or other. But we don't care what it is, we only care that it's negative. Okay. So a double primed of this value of r is negative, and the second derivative test therefore tells us, so by the second derivative test, we know that. So then a of r has a local maximum at r equals 28 over 4 plus pi. Okay. So we're not quite done yet because the question says, what is the maximum possible area? So we just found out where this maximum occurs. Okay, it occurs when r is 28 over 4 plus pi, but now we want to know what is the actual maximum area. So we have to take this value of r and stick it into the area equation here. Okay, so we have to stick it back into this equation here to get the actual maximum area. All right, so I'm kind of out of room over here. So what I'm going to do is flip it over to the back. So a of r equals 28r minus 2r squared minus pi over 2r squared. Okay. And we want to find out a of 28 over 4 plus pi. Okay. So it is going to be kind of messy algebraically, but the answer actually, when we simplify, it's not going to be too bad. But again, why are we doing this? Because we were asked to find the maximum possible area. And we know, okay, we just found out from the second derivative test that that happens when r is 28 over 4 plus pi. That's what the second derivative test just told us. So now we want to find out what is the actual maximum area. So we take this value of r that gives us the maximum area and we stick it into the area equation to get the actual maximum area. Okay, so that's what we're doing over here. Okay, so this is going to be 28 times 28 over 4 plus pi minus 2 times r squared, which is 28 over 4 plus pi squared, okay? And then minus pi over 2 times 28 over 4 plus pi squared. Okay? Now, some instructors, they don't require you to simplify anything, so if you don't have to simplify, this is really an okay answer. We can simplify a little more here, quite a bit more actually, but if you don't have to simplify, that's an okay answer. And that's pretty much it for the video. But if you have to simplify, or if you want to know how to simplify this, we're going to continue on with that. But if not, then that's pretty much it for this video. But anyway, let's continue on with this. So 28 times 28, that's going to be 28 squared. And then on the bottom we have 4 plus pi still. And we have minus 2. So what I'm going to do is rewrite this. So remember that fact that a over b quantity squared is the same thing as a squared over b squared. Okay? So I'm going to use this fact over here to say 28 squared on top, 4 plus pi squared on the bottom. And then we still have a pi over 2 over here. And I'm going to use that fact again, 28 squared on top, and 4 plus pi quantity squared on the bottom. Okay? So now, notice every term has a 28 squared in it, right? So we have a common factor 28 squared we can pull out. But what about on the bottom? 4 plus pi squared, 4 plus pi squared. So we almost have 4 plus pi squared everywhere. So let's do this. Let's multiply this guy by 4 plus pi on the top and the bottom. Okay, so we want to put another 4 plus pi on the bottom, but to make that okay, we have to put it on the top also. So this becomes, first of all, 28 squared. Let's go ahead and simplify that. That's 784. Okay, so 28 squared is 784. And then we still have 4 plus pi on top. And then on the bottom now we have 4 plus pi squared. Minus 2 times 28 squared is 784. And then on the bottom 4 plus pi squared. Okay, and then minus pi over 2 times 28 squared was 784 again. And then on the bottom 4 plus pi squared still. Okay, so now 784, 4 plus pi squared, 784, 4 plus pi squared, 784, 4 plus pi squared. That is terrific because now we can factor that out from everything. All right, and then what's left? Well, over here, 4 plus pi is left. Okay, if we pull out 784 and 4 plus pi squared, then what's left over here is just the 4 plus pi. What's left over here? Just the minus 2. What's left over here? Just the minus pi over 2, right? Because we pulled this whole thing out, so only the minus pi over 2 is left. Okay, now let's simplify a little more. So this is 784 over 4 plus pi quantity squared. And then 4 plus pi minus 2 minus pi over 2. So 4 blah 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 minus 2. Okay, so that becomes 2. And then plus pi minus pi over 2. Remember, pi is just 2 pi over 2. So 2 pi over 2 minus 1 pi over 2 gives us a plus pi over 2. Okay? So, that's looking a little better, right? It's way more compact than this mess up here. But we can still go a little further. So let's push in a 2 inside of this parentheses here. So 784, that's the same thing as 392 times 2. Okay, so why am I doing this here? What am I doing? Well, what I want to do is distribute this 2 into here. Okay, so what's that going to give us? That's going to give us 392 over 4 plus pi quantity squared. Now, if we distribute this 2 into here, 2 times 2 is 4. 2 times pi over 2 is pi. And notice what happens, 4 plus pi on top, 4 plus pi squared on the bottom. So this 4 plus pi cancels with one of these down here, and what we're left with is 392 over 4 plus pi. Okay? And that's our answer here. So the maximum, and that's as simplified as that can be, so the maximum possible area of the Norman window is 392 over 4 plus pi feet squared. Okay? And if you want to know the approximate value of that, 392 divided by 4 plus pi, that's about 54, about 54.88 or 89 square feet. Okay. So the maximum possible area is this mess here, square feet, and then that's approximately equal to this. All right, so that's it for example 4 with applied optimization. So, quite a lot going on there. It's a little bit more complicated than the others just because we have this goofy shape here. So the equations have more to them, so they're a little more complicated. But again, the math is all the same, and the steps are all the same too. Follow these general steps here, everything was okay. The domain is kind of weird. Not well, describing the domain was kind of weird, but it wasn't really too bad. Just remember the geometry of the problem. Okay, you're restricted by the geometry and not necessarily just by the equation. So a lot of stuff going on here, but that's how we work with Norman windows and applied optimization.